Good morning. Can you hear me? Hi, my name is Finalist. I'm a Senior Manager Operation Research at CSX Transportation. I will be co-presenting today with Yanfeng Ouyang from University of Illinois Urbana-Champaign. On this paper, we had 4 more members of our team. Jing Huang, she used to be CSX Transportation, now she works for Walmart. And Yanfeng had 3 PhD students, Xiyang Shi Chen, and Jiaodong Wang. The topic of our presentation is infrastructure planning of mechanical locomotive facilities. And before we jump into the presentation, I really want to thank all of us. We would like to thank the judges and the committee to give us a chance to come here and speak and talk about our work. We are very excited to actually talk about our work. So if I go to the next slide, the UIUC, University of Illinois Urbana-Champaign, you will hear me saying UIUC, and CSX have been collaborating on this project since 2011. And if you look at we have a number of departments working from both sides. On the CSX side, with operations research, mechanical, locomotive management, and process excellence. And on the UIUC side, we had civil engineering and industrial engineering. And mainly, we have been working on various different OR problems since 2007, but on this problem from past 4 years. Before I jump into the project, we want to show you a small video. Mainly has 2 parts. The first part talks about who we are, what CSX does, because there are a lot of non-railroad people in the audience. We thought that would be valuable. And then second part has a testimony from our business partners, vice president, to say how this project has really helped them in their day-to-day decision making. So we'll go ahead and play the video.
CSX Transportation is a leader in the rail transportation industry. CSX's 31,000 employees transport a broad portfolio of products, from coal, new energy sources, automobiles, chemicals, military equipment, grain, and consumer goods. Moving these goods is vital to the U.S. economy. In 2014, CSX transported nearly 7 million carloads and generated over $12.5 billion in revenue. Rail has been a popular method of transportation since the first tracks were laid nearly 200 years ago. Rail is efficient and environmentally friendly. Moving freight by rail is 4 times more fuel efficient than moving freight on the highway. Trains can move 1 ton of freight 480 miles on just 1 gallon of diesel fuel. The rail industry is poised for growth as highway congestion and deteriorating highway infrastructures causes shippers to move to economical and reliable rail shipping. The continued popularity and economy of rail is dependent upon billions of dollars in critical assets. The backbone of CSX's infrastructure is its 21,000-mile rail network that stretches across the eastern third of the United States. This extensive network connects to the global transportation network by interchanging with other major railroad carriers, intermodal terminals, and more than 70 ocean, lake, and river ports. CSX has 200,000 cars moving on its network at any one time, pulled by a fleet of 4,000 locomotives between hundreds of strategically placed yards and terminals. Getting products where they need to go on time and efficiently is a complex job, and CSX relies on leading-edge technology to help.
Hello, I'm Gary Williams, Vice President of the Mechanical Department at CSX. I'd like to personally extend my gratitude to the Informs Committee for this opportunity to share the great work that has been done on the Mechanical Locomotive Infrastructure Project. At CSX, the Mechanical Department supports the repair, service, and fueling of our large fleet of locomotives. Right-sizing mechanical infrastructure is key to improving asset availability and utilization, while reducing transportation and mechanical costs. Prior to this project, the decision-making process around right-sizing mechanical locomotive infrastructure was primarily manual and relied on expert knowledge and experience. This project developed a strategic, fact-based model to aid decision-makers. The project was a joint collaboration between CSX and the University of Illinois at Urbana-Champaign. The model allowed us to run thousands of what-if scenarios to help us in 3 key areas. First, improve efficiencies of the network by consolidating work in fewer facilities throughout the system. Second, identify best locations for opening new facilities to handle increased traffic. And third, forecasting facility usages and productivities under future traffic patterns. The tool that resulted from this project is now an integral part of the strategic decision-making process for mechanical locomotive infrastructure at CSX. It has given us the confidence to invest millions of dollars in major capital projects such as opening new facilities, as well as helping us flex existing infrastructure to meet current demands, resulting in millions of dollars in savings. This project has been a great success for CSX and provides an excellent example of applying operations research techniques to enhance decision-making in practice. Thank you and have a safe day.
Okay, I got it. So like Gary Williams on the video said, the mechanical department at CSX supports the mechanical work on locomotives, and he talked about 3 different types of work: repair, service, and fueling. If you think of from our personal vehicles perspective, they are very similar. So in the personal vehicles, we also get repairs and service and fueling done. So in the locomotive perspective, they are very, very similar, but a little bit different too as well. So repair is needed when locomotive partially breaks down or fully break down. Service is needed to replenish the critical fluids in the locomotive, water, oil, also cleaning toilets, cleaning the cabs, and thus periodical. So repair is kind of stochastic, where it breaks down and you have to fix it. Servicing is periodical. And fueling is done, of course, as the locomotive move around the network. It burns fuel, moving cars. So whenever the tank capacity, whenever the tank goes down, the fuel in the tank goes down, you have to refuel it. So in order to do work on these locomotives in the network, these locomotives are very expensive. If you think about it, the locomotive cost around $3 million to buy, and we have 4,000 of them. So we really want to utilize them as much as possible. Right? But performing mechanical work on these is very important. Otherwise, they will not work. So how do we find opportunities to work on these locomotives is challenging. So if you look at one of the examples, so this for the CSX network was shown in the video. And the dots here represents all the origin and destination of trains on our network. If you pick one train, for example, from New York to Georgia, so that's from Selkirk, New York to Waycross, Georgia. That's about 1,000 miles. And over the route of this train, we may assign more than one locomotive to the train, but we prefer not to change the locomotive all the way to destination. We keep the same locomotives all the destination. But again, locomotives may not have enough tank capacity to go all the way, so we may have to fuel it on the line of road. And it also may do other work. For example, it may stop and change cars. It may pick or drop cars. It may stop again and change crews because crews cannot run the train all the way to Florida. And once it is destination, it may be it gets removed from the current train and gets assigned to a new train. So these are the places where we have opportunity to work, basically. And if you think about these places, I'm going to move out of podium. I feel a little bit uncomfortable. You guys okay with that? Okay, thank you. If you think about it, the opportunity to do work on the line of road is we only have few hours of dwell, right? So if you drop or pick cars or you change crew, you are looking at half an hour to 3 hours of time. Once you arrive at destination, you may be looking at 8 to 14 hours of time for dwell. So on the line of road, another thing is we cannot detach the locomotive. We cannot detach it from the train because it's on the train, right? So we need different types of facilities at these locations. Right? We need facilities which can come to locomotive. At these locations, we can have the locomotive go to facilities. So now we are talking about movable types of facility versus fixed type of facilities. So in order to fuel a locomotive while en route, we can bring facility to locomotive. The example could be a truck. A truck can come there and fuel the locomotive. Or we may have mainline fueling stations, we call them, can come and fuel the locomotive as well. And once it arrives destination, we can have more luxury to take locomotive off the locomotive train and then put it in a facility where we have cranes and we have all kind of things. So we can bring the take locomotive to the facility, or we can also have truck there as well. Not only that, let's say the destination doesn't have this facility, then you may have to go to some other facility and get it repaired there and then come back. So the challenge here is the facilities are not everywhere, and so how do we get this work done? So these are the places where we have opportunities to do work. Again, we talked about these 3 types of work. So if you talk about the facilities, which work can be done at which facility, the repair can be done at shop. Primarily it's done at shop. Servicing is primarily done at service centers. Service centers can also do repair, minor repair. Fueling can also be done at service centers. There's mainline fueling station I just talked about, which does fueling when the locomotive is still attached to the train. And we have trucks which can do servicing and fueling. So you can see this matrix starts getting complicated with many-to-many relationships, where you have repair done at multiple locations, service done at multiple facilities, and fueling also is done by multiple facilities. Not only that, it gets even more complex because the locomotives are of different type, of different manufacturer, GE and EMD. They are different type with different tank capacities, different parts. So now there is a work type which actually is a lot of work types, and the facilities can also be of different capability. So now it gets really, really complicated to assign this type of work to this type of facilities. This is our current footprint of mechanical facilities. It's all over the network. We have around 10 shops, 30 service centers, 29 truck homes, and 3 mainline fueling stations. Now, if you look at the reason why we are working on this problem is, if you look at this graph on the right-hand side, this we call a delta map. This shows traffic on our network between 2013 and forecasted traffic in 2016. And what it shows is that the green line shows you the increase in the traffic volume. The red line shows the decrease in the traffic volume. So this shows that we're going to be increasing traffic on these lines and we're going to be decreasing traffic on these lines. Now, once that happens, of course, our facilities are no longer optimal. So we have to adjust our facilities according to the needs of our demand, of the railroad traffic demand. Right? And that's one of the main reasons why we are working on this project. How do we optimize our footprint to accommodate the needs of the market? Now I would like to give my presentation to Yanfeng, and he will talk about what kind of model we have developed and what kind of solution approach we have taken.
Thank you. As Kamalesh mentioned, this is a problem about deploying infrastructure in the railroad network. And then we actually had the fortune to work with CSX for more than 8 years now, continuously, and had very nice results over the years. And when we first heard about this problem in 2011, we were really intrigued because this problem is not only practically important, a lot of money involved, but also very academically intriguing because it's a very complex problem, which I'm going to explain right now. The problem of locating multi-types of facilities, such as shops and the service centers, obviously reminds us of location problems. And then, obviously, we are trying to deploy facilities to serve spatially distributed demand. And then, there is always a trade-off between investment on the facilities as well as the transportation costs for moving the demand to the service. But then here, that's a little bit tricky. This problem is very complicated, but just a little bit hint. It actually, even how do we move the locomotive is not that trivial. Actually, in the railroad, we learned that there are multiple ways of moving a locomotive. If it happens that there's a train passing the origin and destination, then we can attach the locomotive to the train, and the locomotive travel for free. If there's no such a train passing, then you somehow have to form a light train, I think. Light train is a train with only locomotives. Okay, then you pay a cost for moving them. And then if there's the combinations of that, then we try to utilize as much as we can with the free moves. So actually shipping them is not a trivial task by itself. Then, so if, again, with that, we still have the problem of balancing between the investment cost versus the transportation cost. And then we all know that actually if you invest more in the investment, you reduce the transportation cost. Then the question is, where do you find the sweet spot, right? Then the problem becomes even a little bit more tricky when we consider the movable facilities. Now we have the option of sending the trucks to the site to do the service, rather than moving the locomotive to the facilities. And then the trucks normally sometimes can save costs because it's cheaper to move a truck than a locomotive. But then at the same time, we also realize that actually we need to determine where to build the locomotive homes, which is where the trucks are going to be stored, and how do we route them to serve the demand that's scattered. And then we also understand that actually if we do build locomotive trucks, then we might as well change the location of the fixed facilities. Obviously, they are interdependent, right? So maybe we have another balance of the costs. How do we balance the different investments, right? The problem becomes even more trickier if we consider fueling. Just to take one example, we consider this one route from New York or maybe somewhere from Northeast to Georgia. And then we are given this shipment demand. We need to make sure that this shipment happens, and then we need to make sure that the locomotive is fueled along the way. Then we are given the price of fuel at different locations along the way. The question is, do we have the right fueling facility there everywhere, or do we want to purchase at the high price somewhere? Huh? So there's a trade-off there. Then what we need to do is that we need to determine the location of fueling, the quantity to buy, and how we buy it, from where. Okay? We can buy it from the truck. We can buy it from a fixed facility. We can move the locomotive to the facility to get fuel. So there are a lot of options we can consider. Obviously, as you can see, the decision about fueling is interdependent also on the infrastructure investment. For example, on the northeast corner, we may just deploy a truck to do the fueling because it's expensive there. We just need a little bit of fuel there. Yeah? Then in the middle there, near Virginia, maybe we have to move the fixed facility, maybe the service center, a little bit toward the track, such that actually we can save the cost, right? And then in the south corner, maybe we just reroute the truck to provide the fuel. So depending on the situation, we have a lot of options, and then we can easily see that actually the decisions are interdependent. We all know, since we are here at Informs, we all know that actually this problem seems to be integrating three decisions regarding location, routing, and inventory. The fueling is essentially inventory problem. And then each of these problems are well known to be difficult by itself as NP hard. And then now we are really facing a problem that integrates all three parts together. So it's really, I hope by now you agree it's a difficult problem, okay? But before I actually move on to the models to show how we actually solve the problem, I would like to just show one slide to show how this model can be applied to other problems outside of railroads. Really, the twin sister of railroads are the airline industry. And then the aircrafts also have similar needs for service, for repairs, and for fueling. And they also have the same problem about the price variation across locations and so on and so forth. Huh? So obviously, the model that we develop, whatever we do, could be applied to the airline industry. The next generation of transportation, such as the battery swapping vehicles, we need to build a lot of infrastructures to support the development of this industry. And then there's also a lot of issues regarding how do we supply the batteries, either at the fixed locations or actually we send the batteries to the vehicles. AAA, for example, maybe they will do the service like that in the future, right? And going beyond transportation, we can also think about similar problems in the other contexts, such as retailer industry, and so on and so forth. When we have home delivery, when we have fixed retailer stores, when we have to build the supply chain network, and so on and so forth. Similar problems are all over the world, okay? But now let's go back and try to focus on the problem that we have. How do we solve the problem? So in the next two slides, I'm going to show a little bit mathematics. There's no way I can explain any of this mathematics because there's just not enough time. But the purpose of showing this is just to show you the flavor of the work that we did, and also just to show you the components of the model that we developed. Okay? Just don't worry about the math. But so the objective, we are trying to invest in infrastructure to minimize the cost of investment as well as the service costs. Okay? So we first consider facility construction and setup costs, capacitated facilities. We also consider trucks, which is another type of facility that we invest in. We also consider the cost for moving the locomotives. Remember, we can move them either free or with some cost, depending on whether we have trains passing by. Okay? We consider that also in the model. And then we also consider the fueling cost, which is actually a major part in the operations of a railroad industry. Huge amount of consumption. Okay? So we have all this in the objective function. Then the constraints, just really highlight a high level. We have a whole bunch of constraints regarding location decisions and capacity decisions. Those of you who work on location problems will find this familiar. No need to talk about it. We have a whole bunch of these constraints about fueling. Essentially, we try to make sure that the locomotives will never run out of fuel. And each time we fuel, we'll never exceed the tank capacity. And whenever we reach a destination, we'll have enough fuel to start a next trip. Okay, something like that, a whole bunch of constraints. Then we have some constraints about routing. Those of you who work on vehicle routing problems will find this very familiar. I'm not going to talk about it. Okay, and then actually it's a location routing because we are also deciding the location of the truck homes. And also finally, we have some demand satisfaction constraints that actually integrates. We require that all the demands by each type has to be satisfied. That's all. Pretty straightforward. But then the problem is, it's very difficult still. Obviously, we integrate several difficult problems, as we have shown. But also CSX gives us a very large network. We are not complaining, but it's really a huge problem. It has more than 13,000 nodes, more than 14,000 links, more than 4,000 locomotives. That's running every day. And then we have more than 500 candidate locations. Those of you who are familiar with this, this is a critical size measure. With more than 500 candidate locations for each type of facilities. And we have more than 1,000 even for mainline fueling stations. And this translates to, if we use our model to measure it, translates to more than 10 million continuous variables and 5 million integer variables. No commercial solver can even try on this type of problems with this size. And we even tried some of the straightforward approaches, such as using some of the relaxation and the decomposition techniques, such as Lagrange relaxation and so on. But even with this customized solution approaches, it turned out to be quite difficult and actually didn't give us very satisfactory results. So what we actually did is we studied carefully the structure of the problem and the data and so on. We came up with a sort of an iterative heuristic method to solve the problem, and luckily it worked pretty well. So just a main idea about what we do. Essentially, we observe that actually the demand in the system has two types. One type is so-called, we call path-based demand, is really the fueling. It's really embedded, there's some inventory issues regarding where we fuel and how much we purchase. Right? And there's also issue regarding the so-called point demand. The point demand is essentially all kinds of other demand that's generated in the yards. We need repair, we need service, and so on and so forth. Then if the path-specific demand gets transformed into point-specific demand, then the problem becomes easier. So what we did first is that we solved the joint lot sizing problem to try to convert whatever, based on our earlier work in the past. Then we were able to convert, essentially I want to show the animation again. We are given all these train routes around, and then we try to solve the optimal fueling location for each of them, and then essentially we translate the fueling location, the demand into fixed points and the quantities. And then we merge this demand together with other demands, and then we solve a more traditional location allocation and location routing problem. And then this is, well, actually it's not trivial, but then we run a series of models inside this block here, based on some state-of-the-art methods. So this is sort of the idea, that sort of the high-level illustration of the idea. This actually, and then after solving this, we feed back the solution of the facility and back, and then resolve the whole thing again. So this is iterative, almost like a location allocation type of supply-demand type of iteration. Then this is really, although it's iterative by itself already, but it's just one block of the whole solution process. Even this algorithm wouldn't solve the problem with the original data. So what we have to do is actually we have to do some additional network transformation and scaling, such as actually even this heuristic algorithm can be effectively applied just because of the size. I'll just briefly mention a little bit about some of the ideas, just to show a little bit of flavor. Really, if the first thing we really sort of doing, it's pretty standard, but really just how can we reduce the size of the input data? And then the network is just so extensive, and then so many nodes, so many links, just horrible. So we actually came up, based on our earlier work, we were able to remove some of the links and nodes without affecting the solution quality. Essentially, we equivalently transformed the network into a simpler one. Just to give you a little bit idea, if some part of the network looks like this, where there is a node L with no activity on it, we could potentially transform it into an equivalent one by reassigning some costs and adding some virtual links to it. So they are equivalent. We proved it. This way, we reduce some nodes and some links. Then we also did some other work to try to take care of this light move, free move issue I mentioned earlier, which is really bothersome at the beginning because some people get free treatment, some locomotives get free, some locomotives get cost. It's really bothersome. So the same link can be traversed by different locomotives at different costs, which is bothersome to us. So we actually did some network transformation. I'm not going to get into the details, but then essentially try to make sure that actually some standard algorithms can eventually be applied in this transformed network, taking into consideration light move versus free move. We also did some scaling. Really, the purpose of scaling is really to reduce the candidate locations. Given the hundreds and thousands of candidate locations, the problem is just difficult. So what we really do is that we try to do an iterative procedure to iteratively sample the candidate locations, and we solve the problem with a sample of the candidate location. Based on the information feedback from the solution, we then resample the candidate location. Essentially, we are given the candidate locations, we sample them, and then we solve the problem with the sample, and then we try to change the candidate locations, trim it based on the results we got from here. So these are just some pieces of the jigsaw puzzle that we developed over the past 3-4 years now. Okay. And then, but just hopefully it gives a little bit flavor. We are really facing a very difficult problem, and we are really putting our hair to try to make it work. And we are lucky that it seems to be working. So Kamlesh is going to talk about how it worked.
Sorry for going back and forth. So the way the model can be run is in 3 different ways. A clean slate way where no facility exists today. The base way where we have the current facilities but we are changing them, small changes, capacity and capability changes. And an incremental way where we start with current facilities and how can we modify 1 or 2 facilities, shut down one, open another one. So we could run this model in all these 3 different types of modes. We had a need for running thousands of scenarios to do sensitivity analysis around these 5 major factors. So modify locations around the network, fleet sizes. So we have 4,000 locomotives today. Few years from now, if we increase locomotive count or decrease it, how will that change our facility footprint? The traffic levels, as I showed in one of the maps, the traffic level keeps changing. So if we have different forecasted traffic, how will that change our facility footprint? Repair time, if our facilities get more productive, how that changes our solution. And the failure rates. If you buy new locomotives and they are more reliable, then the failure rates go down. And so we did kind of design experiment and sensitivity analysis and all these different attributes and a need for thousands of runs, basically. And the solution time for the model was anywhere between 5 minutes to 3 hours. If it was a simple problem, it was 5 minutes. If they took like clean slate kind of problem, then it was like 3 hours. But still, it was just 3 hours. So in order to do these scenarios, what we did is we came up with a decision support system where the first thing we did is, of course, prepare data. We use SQL Server to prepare data. We set up these case studies. These are like scenarios we could set up in our database and then the web-based interface. We ran this model in a batch, like in a for loop. We ran this model overnight or over the weekend. We visualize the results on our graphical interface where we have maps, we have tables. You could check, uncheck things, and you can see what's going on. And once we do visualize these results, and then we select some few ones, and then we share with our senior management. And then we are sitting down with senior management, actually chief operating officer, in the room, and we are showing these results, and they are making $1 million decisions right there. That's very, very, very powerful. And then sometimes they say, okay, can we change this? Can we change that? And so it is a cycle. So we iteratively did this for any case studies we did in the past. So some examples of case studies I'm going to show. I cannot show all of them, but I'll just give you some flavor of case studies given the time. So if you look at, these are the 10 shops location we have, and the bubble size shows the capacity of those 10 locations. The bigger bubble has bigger capacity. Now, one thing we did is, okay, given these facilities, don't change the location, but only allow to change this facility to go up or down or change capability. What will happen? So if we did that, that is the result. So if we say unrestricted changes to any of these facilities, it says this facility want to go up, this facility in Chicago want to go up, this facility want to go down, this facility want to go down a little bit, this facility want to go down this a little bit. So if we did that unrestricted case, it came back and say you can save 25 locomotives in the transportation cost. That results into 25 multiplied by 3, $75 million savings if you did that. The second example is very similar example, but this is what we did is we have 4,000 locomotives today. We say, okay, what if I only had 3,600 locomotives next year? What will happen? And I don't want to increase the capacity at my current locations. Again, fleet size reduced means we're going to be reducing the need for capacity, right? So we said, okay, don't increase anywhere else. Just see where I will reduce the capacity. And it shows you can reduce most of the capacity at this location and everywhere, some capacity, a little bit capacity at this location. So kind of gives you flavor. You can try many iterations. That's why we ran 1,000 scenarios. Say, okay, let's do this, let's do that. Let the model decide all the facilities. Let's restrict some facilities, let's restrict this, let's restrict that, right? And then we ran all these scenarios and say, okay, what works out for us practically, basically. Another example I want to show is the sensitivity analysis we did, where we have, if you look at this chart, we have on x-axis traffic percentage change in the traffic. So traffic goes up, traffic goes down. The y1 axis on this side is the cost change, the total cost change. If you look at these colors, we're looking at total cost, the capacity cost, the transportation cost, truck cost, and the fueling cost. And on the right hand side, it shows total capacity change in percentage. And as you see, as we increase in traffic, of course, the cost is going to go up. But if you look at the biggest cost, the fueling cost is the biggest, which goes up if traffic goes up, goes down if the traffic goes down. The main reason is the moment a locomotive pulls more traffic, it's going to consume more fuel. So it's directly correlated to traffic. But other cost goes up too, because once you start adding traffic to a train, you may add 3 locomotives versus 2 locomotives. I think I'm running out of time. So implementation-wise, we did a lot of things in the past few years. Just want to go very quickly. We opened a new shop in Chicago in last year. We consolidated the work in few facilities. I did not put names here just for confidentiality, but we did consolidate the work into fewer facilities. We added additional capability in Cincinnati, Ohio. We added a particular machine there, wheel-through machine we call it. And we expanded capacity in Nashville, Tennessee. And all these resulted into realized savings of more than $30 million. And we think there is a huge potential. If you remember from the video of Gary Williams, he was talking about this model has become a part of, integrated part of their decision-making going forward. And we think we're going to be continuing to use this proactively in future, and we think there's more than $100 million savings forecasted using this model. So to summarize, we think we have solved a very challenging problem. It's a location, routing, inventory problem integrated. And we had a very effective solution framework with decomposition as the main part, but scaling and network transformation. The results are used in the real-life application, of course, on the CSX full-scale cases. And we are doing a fact-based decision-making versus gut-based. Right? Before this model, it's all about gut-based decisions. And we are not saying gut-based decisions are not bad, but we are providing facts to say, okay, how good is your gut, basically. So gut says, I want to open a shop in Chicago, but the fact says you can save 5.5 locomotives if you open a shop in Chicago, or 6 locomotives. We have saved millions of dollars of savings so far, and this became an integral part of decision-making process at CSX. This project has received a Chairman's Excellence Award at CSX. That's one of the most prestigious awards at CSX in 2013. And like Yanfeng mentioned, this work can be adopted by other industries as well. This concludes our slides. Hopefully I'm not over time. Thank you.